Hello, my name is Brad Burris. I'm an Intel Fellow, and I'm leading Intel's IPU and Foundational NIC Architecture in the Networking and Edge group. Our group drives all networking and connectivity for the data center and the edge. I'm really excited to be here today to talk to you about something I'm passionate about, namely the Infrastructure Processing Unit and how it will revolutionize the data center of the future. Our agenda is pretty simple. I'm going to provide a brief introduction to Intel's infrastructure processing portfolio, and then jump into our new 200 gig IPU codename Mount Evans. I'll give you a brief overview of the product, and then I'll walk you through a packet processing example. From there, I'll introduce you to Fpga Based Ipu products. So you should leave here today with a good understanding of what Intel offers in the infrastructure space. Okay. This is our infrastructure portfolio. If you saw the earlier keynotes, you will have been introduced to the values of an IPU, like isolation between the tenants and the service provider, the benefits of offloading the host processor and using more infrastructure optimized solutions, and the changes enabled in data center storage architecture. So I won't go through those again. One thing we know is that many cloud customers are taking advantage of SmartNICs and IPUs today, and that their solution of choice is predominantly Intel. Intel has already been working with some of the world's largest cloud operators to realize these advantages in practice and at scale with FPGA-based SmartNICs and IPUs. We've seen the evolution of the IPU. We started with the FPGA SmartNIC, shown on the right, which is a programmable accelerator delivered through a combination of FPGA and discrete networking products. This was primarily used to move networking data plane off of the host processor, but other offloads are available. As we worked with our cloud partners to migrate other workloads like storage and their associated control planes from the host to the NIC, we created a new class of NIC we call an IPU, or Infrastructure Processing Unit. This provides the same acceleration capabilities as a SmartNIC, but adds the ability to run applications and control stacks on the device. As you can see, Intel offers two kinds of IPUs. The first kind of IPU is an FPGA-based, which enables faster time to market features and tremendous flexibility with some cost of power and performance. Today, Intel offers our 50 gig Big Springs Canyon IPU, and will soon be introducing a 200 gig Oak Springs Canyon in this category. The second kind of IPU is a dedicated ASIC SoC, which is optimized for power and high performance across networking, storage, and other infrastructure workloads. The choice of IPU type is a function of workload, flexibility needs, and constraints such as power, performance, and form factor. At Intel, we believe each of these product categories has a role to play in the ongoing transformation of the data center. Okay, so now let's dive into the Mount Evans IPU. Mount Evans is our first ever ASIC IPU, supporting throughputs of up to 200 gigabits per second. First and foremost, Mount Evans is designed to work as for the world's largest clouds. As Pat Gelsinger and Amin Vedad announced earlier today, we have architected and developed Mount Evans hand in hand with Google as our partner. This has provided tremendous insights across the board, from use models to deployment scenarios to performance requirements to lifecycle management. Second, Intel has been working closely with other cloud providers like Microsoft, Baidu, JD, and others for several years through Intel's IPU programs. And our learnings with those products has influenced many of the Mount Evans architecture and design trade-offs. Third, Mount Evans has been designed for performance at scale under real-world workloads and not just benchmarks. This is critical for the cloud operators. And finally, in order to be hyperscale ready, we designed in security and isolation from the ground up throughout the chip. On the technology front, Mount Evans is loaded with innovation. To start with, the focal point of the product is what we believe to be a best-in-class packet processing engine that supports a large number of existing use cases like vSwitch offload. Another technology, created by extending Intel's proven high-performance Optane NVMe controller, enables Mount Evans to emulate NVMe devices. A third innovation I think will prove incredibly valuable is a next-generation reliable transport protocol. Built in collaboration with Google, this technology solves the long-tail latency problems that exist with a lossy network. And lastly, a fourth enabling technology that can be used across a variety of use cases is our advanced crypto and compression accelerators. We recognize that IPUs won't be a compelling technology without broadly enabled software. Otherwise, they will remain a niche, albeit a large niche, at the top cloud providers. This is why we've had our eyes set on enabling software developers to do what they do best, namely, create new solutions by building a rich software developer ecosystem. We start with innovative performant hardware designed for flexibility and ease of programmability. We add to this the expertise that came in through our Barefoot acquisition, driving the use of the P4 language in the industry as a standard framework for programming network data planes onto IPUs. With Linux as the foundational OS, we leverage and extend well-known SDKs and frameworks like DPDK and SPDK, and have introduced IPDK today. We think this marriage of ecosystems for networking and storage with the new Infrastructure Programmer Development Kit will really help kickstart the broader IPU ecosystem. Speaking of the IPU ecosystem, Mount Evans is Intel's IPU that is working with VMware and others on Project Monterey to bring the value of IPU to telcos, hybrid cloud, and edge. Okay, let's dive a little deeper into Mount Evans. Here I'm showing a high-level block diagram. As you can see, Mount Evans is organized with the network subsystem on the left and the compute complex on the right. While we call it the networking subsystem, this is really the data plane processing logic across all of our inline use models. And while I can't do an in-depth review of everything in our short time today, I did want to give you a flavor of the design in the next couple of slides. The Mount Evans network subsystem supports 200 gigabits per second of throughput, supports connections from 1 to 4 hosts, and while Mount Evans is host architecture agnostic, I personally recommend a Xeon. In order to support cloud scale deployments, we've designed Mount Evans to support thousands of virtualized interfaces that enable large numbers of VMs or containers. One of the major movements in large clouds is a shift away from legacy networking like TCP to other protocols that deliver data with more predictable latency and increased performance. This is driven by applications like storage, artificial intelligence, machine learning, and fast messaging. Mount Evans supports this with implementations of both RockyV2 and the new reliable transport technology we've developed with Google that I mentioned earlier. Beyond being optimized to solve for tail latencies with lossy networks, the reliable transport technology can support multipath routing and also provides advanced congestion control capabilities. So we are really excited about the value of both protocols. Our Intel Optane-derived NVMe engine exposes high-performance PCIe NVMe devices to the host processors. This enables infrastructure providers to use the IPU to implement their storage protocol of choice, whether it is a hardware-accelerated NVMe over fabrics or a custom software backend on the compute subsystem. In order to optimize the software backend, we've implemented all of the virtual machine quality of service and rate limiting in hardware, and provide a flexible load balancer to hand work items to software. This design supports locally attached storage, fully disaggregated storage targets, or a hyperconverged infrastructure. One of the most impressive parts of the Mount Evans design, Intel's programmable packet processor, delivers leadership support for use cases like vSwitch offload, firewalls, and telemetry functions, while maintaining support for 200 million packets per second on real-world traffic. This is enhanced with a fully featured transmit traffic shaper. And finally, with our security-first mindset, Mount Evans provides features like root of trust, secure boot, and inline IPsec to secure every single packet being sent across the network, even if it's over millions of connections. On the right-hand side of the chip, our compute complex is built on the ARM Neoverse architecture using the N1 or Aries core. Yes, I did say ARM. We took a look at the available compute options, and the N1 met our design requirements. These 16 cores running at up to 3 gigahertz, are backed by a large 32 megabyte system level cache and 3 dual mode LPDDR DDR4 controllers that can provide up to a theoretical 102 gigabytes per second of memory bandwidth. Together, these give Mount Evans the bandwidth and horsepower to take on large infrastructure workloads. The compute complex is tightly coupled with the network subsystem, allowing the NSX accelerators to use the SLC as their own last level cache. The mesh provides high bandwidth, low latency connections between the two sides, and this enables a flexible combination of hardware and software packet processing. Our look-aside crypto and compression engine is derived from Intel's Quick Assist technology that you can see in the Intel Xeon roadmap, but we've made significant modifications to it for our IPU use models. This includes support for the Z-standard compression algorithm, which is the emerging best-in-class standard in the cloud. And the engine is accessible from the attached host or the ACC cores. Finally, our dual-core management processor provides a secure way to interface the platform and the orchestration layers, supporting robust system manageability. As you can see, this chip took out all the stops to deliver a high-performance, very flexible IPU. The Mount Evans packet processor is a richly featured engine designed to handle a huge variety of use cases. While we have proven that this engine enables key Google use cases like the Andromeda infrastructure framework, the packet processor is designed to be generic, with flexibility and scale headroom built into each component. The packet processor is recirculant, enabling pipeline extensions without sacrificing performance. This enables a programming model for full data plane offload instead of taking a cached or flattened pipeline approach, such as is traditionally done for OVS OpenFlow tables. Our whole pipeline approach enables a more capable offload model built on top of a P4-based programming strategy. In terms of raw capability, the Mount Evans packet processor brings a wide set of tools to the table. Its packet editor and parser are generic and fully programmable, with no protocol-specific fixed functions. Its classification engine includes a wide list of primitives: exact match, wildcard match, range match, and longest prefix match. From a scale perspective, DDR backing enables table sizes up to 10 million entries and support for auxiliary table functions, such as hardware-driven aging and hardware-driven auto-insertion. These kinds of features are absolutely critical to achieving high performance in a real data center. One of the strengths of the Mount Evans architecture is its close coupling with the compute complex. The ability for the packet processor, as well as other agents, to directly interact with the compute mesh and associated system-level cache provides tremendous performance and usability advantages. Lastly, metadata is a key feature of the Mount Evans packet processor. Generic metadata enables a number of chained packet processing models, creating many ways by which the packet processor can accelerate control software on the compute complex, from descriptor-level insertion to packet-level hint prepending. The best way to see the packet processing capability in action is to look at a specific use case. We decided to look at a critical edge workload known as a next-generation firewall. Though the exact pipeline is synthetic here, it closely approximates how many firewall appliance vendors may choose to use Mount Evans. A next-generation firewall is a network function that includes a standard Xeon CPU. By using an IPU with the Xeon, it is possible to create a higher performance and much more feature-rich solution. Our example will focus on the Mount Evans packet processor, but other parts of Mount Evans apply here as well. This could include your security layer, either running IPsec in our inline accelerator or a TLS proxy running on the Mount Evans compute complex. With next-generation firewall, the central data plane function includes a combination of the Mount Evans packet processor and a stateful deep packet inspection pipeline on the Xeon. Since firewall policy can run the gamut from simple stateless IP filtering and L4 filtering rules to deep HTTP processing rules, the Xeon host plays the role of control agent, offloading policy rules into the Mount Evans data plane while reserving the Xeon soft data plane for layer 7 and deep packet inspection cases. Going a little deeper, the Mount Evans data plane begins by handling any network virtualization termination. This includes the parsing, lookup, and termination of encapsulated headers, such as NSH or VXLAN, which can be parsed, processed, and edited out at 200 million packets per second. Custom option headers, which can be common for some NSH deployments, are easily supported. Next, the packet engine must perform a lookup to determine the offload policy. These can be a combination of lookup types, typically exact match, but also with embedded range lookups. An exception here suggests the policy is handled by the soft data plane on the Xeon host, and the exception path routing may perform additional lookups and packet edits to enable hints or metadata for use by software. Next, for offloaded policy rules, the packet engine implements the inline policy function as well as any associated logging or telemetry operations. Again, the inline function can take full use of any primitive, from LPM to range mesh as needed. Finally, for both exception path and offloaded policy rules, the packet engine must perform post-processing. This includes initiating any encapsulations related to outgoing tunnels, as well as performing any routing lookups needed on the outbound path. This entire pipeline is fully customized using P4, and this model pipeline can execute on the Mount Evans packet processing hardware at the full 200 million packets per second, regardless of the specific type of protocols at play. This example also highlights the use of recirculation to extend the physical pipeline, again with no performance hit. Hopefully this example helps you understand why we're confident the Mount Evans packet processing offloads will satisfy most use cases out there. If I had more time, I would have walked you through a simpler example of how to offload the vSwitch. Due to the duration, I've decided to skip this one, but I did want to stop and say that Mount Evans packet processor can completely offload most vSwitches, like OVS, completely into hardware. So that was an overview of Mount Evans and a deep look into packet processing. Now let's talk some more about Intel's Fpga Based Ipus. As I mentioned previously, we've been engaged with many top cloud customers over the past several years, working on our FPGA-based SmartNICs and now on IPUs. Our current product is known as Big Spring Canyon. This supports 2 ports of 25 gig and is based on an Intel Stratix 10 FPGA, which provides performant flexibility, and our Hewitt Lake generation Xeon D processor for software. For many customers looking to migrate from a VMM emulating the NIC to an offload solution, you want to leave the tenant VM unchanged, so all of the Intel IPUs support VirtIO. The beauty of the Xeon D-based processor is that you can easily migrate your workloads running on Xeon SP today down into the IPU. Coming soon, we will be offering our 200 gig Oak Spring Canyon. In order to achieve the 200 gig throughput, we take our latest generation Agilex FM7 FPGA and add to it an Ice Lake generation Xeon D. Aside from higher performance and better power, the Agilex device also provides hardened crypto acceleration. Okay, let's talk about the FPGA use cases. As shown here, you start with the FPGA effectively acting as a bridge between the tenant running on the host and the vSwitch data plane running on software on the Xeon D. Each tenant is assigned its own virtual functions, for things like networking and storage, and the logic that used to run in the hypervisor on Xeon that emulated the VirtIO devices has migrated into the Fpga. Ultimately, the Fpga hands the packet or storage transaction to the Xeon for processing. The Xeon can do things like vSwitch data plane and the associated control plane, as well as other key workloads like a storage backend, such as NVMe over TCP. When done with the processing, the Xeon will send the packet back to the Fpga, which provides the basic packet processing and sends it out to the wire. Intel provides the pictured IP building blocks in the Fpga and has a library of available example software. You can see some of those examples on the slide here that can be used to jumpstart your development. The beauty of this solution, of course, is that the infrastructure provider can implement any service they want in software running on the familiar Xeon processor. So it's a really easy framework to get started on. With the Fpga Based Ipu, you can add your own value to the Fpga design. The Canyon architecture allows developers to migrate more functionality into the Fpga over time. So if you want to harden the vSwitch to free up Xeon cores for a new service, develop the RTL, load it into the Fpga, and you are off and running. Or maybe you have a great idea for inline network analytics, but it has to keep up with wire rate. Again, this is an ideal platform. The Fpga even has its own dedicated DDR memory. Ultimately, you are only limited by the complexity of your solution and the total Fpga resources available. By shifting workloads from the Xeon into the Fpga, you can achieve higher performance and free up compute resources that can then be reinvested in new software features. Intel supports the developers by providing Fpga offload example kernels with designs for your virtual switch, Rocky v2, or NVMe over Fabric. There are also production pass-through solution partners. You can see why the Canyon architecture has been successful in the marketplace. As I reach the end of my talk, I'd like to leave you with a closing thought. Intel is firmly committed to winning the data center with our Fpga and ASIC-based IPUs. We believe this is an important compute element in many deployments going forward. This is why we have worked closely with the top cloud providers for the past several years and continue to grow our IPU capabilities and our portfolio. As a result, Intel is the volume leader in the IPU market. We've deployed Fpga-based designs in high volume with Microsoft Azure. We have announced Fpga partnerships with Baidu and JD Cloud. And also, announced here earlier today at Intel On, we revealed that our first generation Mount Evans Ipu was co-developed with Google. And we announced at VMworld just a few weeks ago that, in partnership with Dell and VMware, through Project Monterey, we will be expanding the reach of Intel's IPU portfolio to the hybrid cloud, telco, and the edge. And those are just the engagements we can share. It's a really exciting time to be here, looking out at the transformation that Intel and our portfolio of IPUs will use to drive the data center of the future. I encourage you to put on your developer hat and help us shape the future. Finally, I encourage you to take advantage of the other segments of this event to learn more about our IPU products and by visiting intel.com/IPU. I also recommend taking advantage of all of the IPDK sessions to learn what the excitement is about. Please check out IPDK.io. Thank you very much.